Good evening, guys. I hope everybody had an amazing weekend and a really good Halloween. Today we're going to start talking about Newton's second law. And I had planned on doing a PowerPoint for this, and then I realized that the majority of this is really just going to be me doing practice problems. So a PowerPoint was kind of superfluous. So, Newton's second law. We talked about Newton's first law before, and the first law was the law of inertia. Newton's second law is really just an equation, and it says F equals ma. Now, more specifically, it says the net force equals the mass times the acceleration of the object. So what this equation is saying is that if I apply a net force to an object, it's going to accelerate. The heavier that object is, the less it will accelerate with the same force. So we're going to explore this relationship a little bit today. Before, we've just been worried about objects that are in equilibrium. And that means that, of course, all of the forces are balanced out. So now we're going to look at objects that are not in equilibrium. We're going to look at objects that are accelerating and that are experiencing a net force. So before we do this, we need to have a quick discussion about friction, because friction becomes important when things start to move. We have two different kinds of friction, just like we had two different kinds of equilibrium. We have a static friction, and we have kinetic friction. Static friction is the friction that exists between two surfaces when the objects are at rest. Kinetic friction is the friction that exists between two objects when one of the objects is in motion. So, static friction will always be greater than kinetic. And so when we talk about static friction, a lot of times we say Fs. Static friction will always be greater than your Fk or your kinetic friction. And when you think about that, that kind of makes sense. If you've ever had to try to move heavy furniture or anything that's heavy in the first place, it's always more difficult to get the object moving than it is to keep it moving. So that initial push or that initial effort that you put in, that initial force that you apply, will always be greater to actually get the sucker in motion at first. And then once it's already sliding, you don't have to apply as much force to it to keep it in motion. So the kinetic friction will always be less than your static. All right, the other thing we have to discuss is something called the coefficient of friction. Now, the coefficient of friction is a ratio, and when we talk about the coefficient of friction, we use this crazy little symbol. It's called mu. It is the Greek letter m. It looks like a really exaggerated curvy M or U. Anyways, it's called mu, and it's a ratio between the friction and the normal force. So what that means is that objects or situations that have higher coefficients of friction mean that there is a lot of friction present in that situation. So the coefficient of friction is just a way for us to discuss, okay, how much friction is happening in this picture? Is it a lot? Is it a little? The coefficient of friction will typically be between 0 and 1. A value of 0.1 is a very low coefficient. So this might be the coefficient of friction that exists between, say, like two pieces of ice. And then a coefficient of friction that's very high would be something like 0.9-ish. And this might be like, for example, tennis shoes on carpet or something where you're going to have a lot of friction present. You're going to have a high coefficient of friction. So there's no units for your coefficient of friction. It's just a ratio between the amount of friction present and the normal force acting on the object. So let's do a couple of examples using F equals ma and this new idea of friction. So I guess the last little thing I have to say when it comes to the friction thing is we talked about there's two frictions, coefficients of friction. There's static and kinetic. So we have a coefficient of static friction and then a coefficient of kinetic friction. And you solve them the exact same way. They're both just the friction divided by the normal force. So let's do a couple of examples, kind of get our feet wet, so to speak. So let's say I have a piano, and I'm going to push the piano across a carpeted floor. Let's say the piano has a mass of, I don't know what's a heavy mass for a piano. Let's say a mass of 500 kilograms. And the coefficient of friction let's say kinetic, let's say it's already in motion. And the coefficient of kinetic friction is 0.4. So if I apply a force of, let's say, say 3,000 newtons, what is the A? Which is a lot of force to apply, by the way, but it's going to have to be done because it's a really big piano. So always, first of all, draw your free body diagram. It's really going to become important now that things are no longer at equilibrium. You guys really need to get in the habit of drawing this free body. So I have normal force going up, gravity down, force applied, my 3,000, and then my force of friction, my kinetic friction, because the object is being pushed across the floor. Alright, so after you draw your free body, go back and label it with the values that you know. You know that the weight of the piano is 5,000 newtons because it weighed 500 kilograms, or the mass was 500 kilograms. And the normal force is 5,000. Your applied force is 3,000. So I need to figure out what my friction is. They told us in the problem that my coefficient of kinetic friction was 0.4. And that is equal to your frictional force divided by your normal force. So now I have 0.4 equals the frictional force divided by 5,000. That's going to get me a frictional force of 2,000 newtons. So now I'm going to come back up here and I can fix my free body here so that I know, because I know what my frictional force is. Alright, so my piano is in equilibrium vertically, right? I have no gravity and I have the normal forces will cancel out. So all I've got left is 3,000 going to the right and 2,000 going back. That leaves me with a net force, or a total force net, of 1,000 newtons. Newton's second law says F equals ma. So my mass is 500, my force is 1,000, which means that my A, acceleration for this piano, would be 2 meters per second squared. Okay, let's look at a different situation. Okay, let's look at another example. Let's look at an example of an object that's going to be on a ramp. because we did a lot of ramp stuff. So this should be hopefully not so bad. So let's say we have a ramp, and let's say we have an angled ramp is 20 degrees. And let's say this is a box, or it can be a kid, I guess, sliding down a slide, a rather square child. Let's say the mass of the person is 40 kilograms. And let's say that the coefficient of friction between the person and the slide, let's say it's kind of a slippery slide. Let's say it's 0.2. So I would like to know, what is the acceleration of the student or the person as they slide down the slide? So, always, always, always draw your free body diagram first. And I'm going to do that with a different colored ink so you guys can see it a little bit better. So we got gravity, and we got a normal force here. Now, they tell us we have a coefficient of friction, so if the kid is going down the slide this way, friction always opposes your motion, right? So the friction's going to go up the slide. So we can go ahead and label what we know. I'm going to redraw the free body over here a little bit so I have a little bit more room. So gravity, normal, friction. Alright, you can just imagine that there's that ramp going down here. Now, I've said it before, and I'll keep saying it, but whenever you have objects at a ramp, on a ramp, you should really sketch in your vectors for your gravity triangle, because the normal is going to oppose the vertical part, and the this part of your triangle is going to oppose your friction. So, we know that the weight is 400 newtons here. I don't know what the normal force is because it's on a ramp, right? So I have to find this side of my triangle. So we can go ahead and do that. My normal is going to be mg cosine theta, which is 400 cosine 20. And then I'm also going to find this side of my triangle, which doesn't really have a name. I mean, I call it the horizontal component of gravity, or sometimes I'll call it the FGX, or sometimes you'll see it referred to as the parallel component of gravity. But I guess whatever you feel comfortable calling it, parallel to the ramp component of gravity. All right. And then that is equal to mg sine 20, or 400 sine 20. So I can go ahead and find those two pieces of my triangle. Ooh, I am not in degrees. Hold on. Okay. So that means that my normal is 376. And my, because this is 376 newtons. And then this little horizontal part here is 137. Okay. Now, you have to remember that this thing is sliding down the ramp, so the friction is no longer equal to this horizontal part that we have right here. We have to solve for the friction. So the friction is going to be equal to the coefficient, friction over normal force is equal to your coefficient. So I think the numbers I made up might be slightly off. Times, no, I think we're okay. Okay. So your normal force then, in this case, your coefficient is 0.2, and your normal force is 376. Be very careful you're not putting in 400 because this thing is on a ramp and the normal force is slightly less because it's on a ramp. So that means that my frictional force is equal to 75.2. Which means this arrow is 75.2. Let's go down a little bit. Okay, so now this is my picture, right? I can redraw it if I want to, a little bit flatter and a little bit easier to read, I have 376 up, I have 137 down the ramp, I have 75.2 newtons of friction, and then I have 376 down here. Remember that whenever we find our components of gravity, we can just take that vector out of the picture completely. Alright, so that means that my vertical forces are going to balance out, and my net force will end up being 61.8 newtons down the ramp. So if that's our net force, we have a net force expression like this. Our net force is 61.8. Our mass is 40. So that tells us that the acceleration of the kiddo is 1.55 meters per second squared. Alright, I think these two examples are a good place to start. We'll probably do some more examples in class, and I'll have another video for you guys with other Newton's second law problems to practice with. Alrighty, I'll see you guys on Monday.